Let's start with a right triangle with the base of 12 and the height of 9. And in it we will inscribe two congruent circles that are touching, just as shown in the sketch. Now, the question is it possible for us to find the combined area of these two congruent circles? If you want to try this interesting problem for yourself, this would be a great time to pause the video and then come back and check the solution. Alright, so let's solve this one. First, we will mark all the vertices of our right triangle as A, B, and C. Then we will mark the centers of our two congruent circles as O and P. Now we will label the radii of both of these circles as R. Then we will rotate the radius of the left circle vertically. As you can see, it will intersect the height AC at the point which we can label as D. The angle at the point D must be the 90-degree angle. We know this by using the tangent of a circle theorem. Just to remind you, this theorem states that if we have a circle and the tangent, and if we pull a radius to the intersection point between the tangent and the circle, the angle between the radius and the tangent will always be the 90-degree angle. So we can use this in our case here, since the line AC represents the tangent of our left circle. Let's continue on by rotating again the radius of our left circle horizontally, but this time to the right. Then we will rotate the radius of our right circle horizontally, like so. Then, for the final time, we will rotate the radius of our right circle, this time vertically. Here you can notice that it will intersect the base of our triangle at the point which we can label as Q. Now here we will again use the tangent of a circle theorem, since the line AB is tangent to our right circle. This means that the angle at the point Q will be the right angle as well. Now let's set our attention to this quadrilateral ADPQ. You can notice that it has three right angles, so that means that the angle at the point P must also be the right angle. From this, we can conclude that ADPQ is actually a rectangle. We can use this in our favor. We can notice that the line DP has the length of 3r. So, if we slide it down, we can conclude that line AQ must also have the value of 3r. The same thing applies for the line PQ. If we slide it to the left, you can see that the line AD also has the value of r. Now, from here, we will try to find the line QB. As you can see, this line will be equal to the difference between the base AB and the segment AQ. Now we can substitute our values and we will get that the line BQ is equal to 12 minus 3r. Now let's pull another radius of the right circle from the point P, but this time to the hypotenuse CB. And we will mark the intersection point between the circle and the hypotenuse as E. Again, we will use the tangent of a circle theorem, since the hypotenuse BC is the tangent to our right circle. That means that the angle at the point E must be the right angle. Alright, so now we will use one really nice property of a circle, which states that the length of a tangents from an external point to a circle are equal. As you can see, we have the same situation on our sketch. We have our right circle and we have the tangent QB. We also have the tangent BE, which starts from the same external point just as the tangent BQ. So from this property we can conclude that the line EB is equal to the line BQ and it also must have the value of 12 minus 3r. Alright, so let's continue by noticing our right triangle ABC. We can use the Pythagorean theorem to find the hypotenuse CB. So CB squared must be equal to the leg AB squared plus the leg AC squared. We can substitute our values and we will get that CB squared is equal to 144 plus 81. This equals to 225, which means that CB is equal to square root of that, which is equal to 15. Alright, so now since we have our hypotenuse, we can try to find the length CE. This length will be equal to the difference between the hypotenuse CB and the segment EB, which we got earlier. So we can substitute our values and get the following. From here we can simplify and get that the line CE is equal to 3 plus 3r. Alright, so for the final time we will try to find the length of the line DC. As you can see, this line is equal to the difference between the height of the triangle CA and the segment DA. So we can substitute our values and we will get that the line DC must be equal to 9 minus r. So now let's pull a new line from the point C to the point P. And this line will form the right triangle DCP. We will now use the Pythagorean theorem on this triangle and we will get that the hypotenuse CP squared is equal to the leg CD squared plus the leg DP squared. We will substitute the values from the sketch and we will get the following equation. Now we can notice another right triangle CPE. We can use the Pythagorean theorem on this one as well. So hypotenuse CP squared is equal to CE squared plus PE squared. We will again substitute our values and get this new equation. You can probably notice that both of these equations have the same value of CP squared. That means that both of them must have the same value. So now we can develop this equation by using the square of binomial and we will get the following. Here we can cancel 9r squared on the left and the right side of the equation and we can do the same for r squared. Now, if we group the common terms, we can simplify this equation as following. From here we will get that 36r is equal to 72, which means that the radius for both of our circles is equal to 2. Now it's pretty easy to find the combined area of these two circles, since this area is equal to 2 times the area of one circle of r squared pi. We can substitute the value of r and get the following, and from here we will get that the combined area of our two congruent circles is equal to 8 pi squared units, and this is our solution. Well, I hope you guys enjoyed this interesting problem. If you did, leave a like and subscribe to the channel for more content like this. Of course, if you found another way to solve this problem, please share it with everyone in the comment section below. And of course, until next time, see you all and take care.